Next hour, hope you've all got the handout for lecture 24, this is now. So we're going to continue discussing the camera geometry and how you can reason about scenes from multiple points of view. In particular, this hour we're going to look at something called the epipolar geometry and how the so-called epipolar constraint helps us make more robust correspondences between a pair of views taken from calibrated cameras. And then we're going to see how this epipolar constraint can be expressed mathematically using something called the fundamental matrix. Okay, and we're going to see how these extrinsic and intrinsic parameters that we've been talking about are encoded into the fundamental matrix, including these other things called the essential matrix, which basically encodes the extrinsics. And then we're going to see how this fundamental matrix can be estimated from point correspondences, and we're going to talk about how we can derive that linear system to do that. So there's quite a lot in this deck. I hope we'll get through it all in the hour. If not, we'll finish it off next time. So, okay, let's just recap then on our camera geometry. I won't spend too long on this because it was literally the last hour for those in the room. So we have a camera that has its center of projection at some offset t from the origin of the world coordinate system being expressed here in by these red arrows. And then what we have is a camera that is rotated at some arbitrary orientation defined by some rotation matrix R. T and R then are the extrinsics, and that camera is imaging the world subject to some internal parameters which are the focal length and the optical center, which is D, and then Cx and Cy for the optical center respectively. And we're going to say that point P, previously we were saying that point P that's being imaged in 3 dimensions is x, y, z, and that the image of that point is p prime or with components u and v. Right, as I say, the intrinsics are the optical center and focal length, and the extrinsics are the rotation, which could be, for example, a 4x4 matrix in homogeneous form, and that offset of the central projection is a vector t, which can also be encoded within a 4x4 matrix, which we'd call big T. Right, we see all these boxes, I won't dwell on them, but these are the two important sets of equations, as I say, that go from 3D to 2D and 2D to 3D, or ray. And we saw last time how we can use the latter box of equations to triangulate two rays. Let's talk this hour about how we can do something else that's useful, which is how we can create point correspondences between a pair of views. Now, we saw before how important it is to be able to create point correspondences between a pair of views or multiple images of a scene. For example, when we were stitching images together, these kinds of things. But generally speaking, if we wanted to track an object across multiple views, or indeed do some sort of 3D processing, it's a useful thing to be able to figure out, given a point in one image, where is that point in the other image? It's the matching between views problem. Well, a trivial way to do that would be to say, well, okay, let's look at the point in viewpoint number 1, which in this diagram is the left-hand view, and let's cut a window, like a little template, and then sweep that window across all possible locations in camera viewpoint 2, and figure out, using maybe something like normalized cross-correlation, which is the most likely location of that point in camera viewpoint 2. I mean, that would be one way of doing this, right? But that search that we're performing there in the second viewpoint doesn't exploit any information we might know about the camera geometries, the relative camera geometry in that scene, which would be available to us if we had calibrated cameras. So if we do know the camera calibrations, i.e. the extrinsics of the cameras and the intrinsics, then we can do better by considering something called the epipolar constraint. So what is the epipolar constraint? Well, obviously, here we have our point on top of the tree being imaged by two views. By the way, instead of calling them viewpoint 1 and 2 in this lecture, we're going to call them the left and the right-hand viewpoint. It doesn't mean they have to be physically located on the left or the right, but it just makes the maths a bit easier to follow if I write L and R instead of 1 and 2. Okay. So this is just a terminology that's used quite a lot actually in computer vision, the left and right camera, but it just means viewpoint 1 and viewpoint 2. Okay. Well, okay, let's suppose that we were viewing this point just from the left viewpoint. Okay, well, if I were looking at the scene just through the left viewpoint, then all the possible locations that point could be will lie along this light ray. Okay, so they could be here, or it could be here, or it could be here, or here. Oh, not here because I haven't drawn it. Any of those 4 locations, or indeed any of the infinitely many locations along that light ray. Okay, but if we were to look at that point from the right-hand camera, we would say that, okay, all of those possible locations that the point could be in space that we've discerned from the left-hand camera, they would lie upon a line. And that is the line of that light ray imaged from the right-hand camera. Okay? If you want to think about this in very concrete terms, imagine having a laser pointer you've shot from the focus of the left-hand camera through the imaging plane out to that point. That's your light ray. If you were to look at that laser pointer's trace from the right-hand point of view, it's tracing out a line. And that's the line of all possible locations of that point, according to the left-hand camera. And that line that's being traced out from the perspective of the right-hand camera, we call that the epipolar line. Yeah? So a point imaged in the left-hand camera corresponds to a line of possible locations from the viewpoint of the right-hand camera. Yeah? And if we add an extra line into our construction here, which we're going to call the baseline, which is simply just the line that connects in 3D the 2 focal points of the cameras, then actually what we're tracing out here is a plane, a triangle in 3D space that we call the epipolar plane. That triangle has 3 vertices. It has the location of the point P and the 2 focal points of the camera. And all of the possible locations of P viewed from the left hand, so according to the left-hand camera, but viewed from the right hand, are all points along that far edge there of the epipolar triangle plane. And you can see that actually it's the intersection of that plane with the imaging plane on the right-hand camera that forms that epipolar line. Can you see that? Yeah? That's a triangle in 3D there, that epipolar plane. It has to be a plane, it's just a triangle in 3D. So all of the rays of light, and indeed the epipolar line itself, lie on the epipolar plane. The epipolar plane is intersecting the camera plane, the image plane of the camera, in order to create the epipolar line. Yeah? And the same is true the other way around as well. We could have viewed that point from the right-hand camera and considered all possible locations along the right-hand ray, and they would have traced out an epipolar line in the left-hand view. So a point in the left-hand image corresponds to a line, the epipolar line, in the right-hand image, and vice versa. Okay? And that is what we call the epipolar constraint. If I view a point from one point of view, I know that the possible locations to match that point in the right-hand view, actually it's a one-dimensional search along a line, not a two-dimensional search around all possible locations in that image. It's a one-dimensional search. The other thing to note is that if you were to consider all three-dimensional points in the world, and the epipolar lines formed by speculating about that point's position in one image with respect to another image, then all of those epipolar lines that are formed would all intersect at a point where the baseline crosses the camera plane. And we call that the epipole, which is the point shown in red there. So all the epipolar lines that would be traced out by picking other points in space other than the top of that tree there would generate epipolar lines that cross the epipole. And this setup of the epipolar plane, the consequent epipolar lines, and the epipoles, this is what we call the epipolar geometry. I'll show you a quick demo. So this is some code I wrote a while back for a collaborative project and I'm going to load up two images here of somewhere I went on holiday once, and then we're going to find some features in these images. And actually, what this code does, it just calls calls the OpenCV library to find CIF points. Okay, so they're all the CIF points that have been found, the key points, and then what we're going to do is establish some correspondence between those CIF points, okay, in the two images. And actually what's happened here, via an algorithm we'll cover later on in this hour, or possibly the next hour, is during the process of estimating these point correspondences, we've also estimated this 3 by 3 matrix, which has a special name. It's called the fundamental matrix, and it describes the mapping of points in one image to lines in the other image. In other words, it encodes the epipolar constraint. We'll come back to the algorithm for doing that later on, but I just wanted to show you for now some examples, just picked at random from those point correspondences, where we have a point in red in one image, and the corresponding epipolar line, which has been drawn in yellow in the other image. And you can see that the point in one image in red, and its corresponding point in red in the other image, that corresponding point lies on the epipolar line, which shows us that the estimation of this fundamental matrix that describes this geometry is correct. Okay, and similarly, points in the right hand map to lines in the other hand that intersect that point well. Yeah. So, for example, if I were to point to, wrong mouse, I were to point to this point here, for example, has been corresponded correctly to this point here. And this point here is given rise to this yellow epipolar line, and this point here is given rise to this yellow epipolar line. You can see that the points lie on the epipolar lines on each view, so this is a good estimation. Okay, so this 3 by 3 matrix here is called the fundamental matrix. Fundamental matrix is going to be the topic of this talk. If I have a point, and it has the location u, v, as we've been talking about, and we express it in homogeneous form, like this, and let's say we're going to call it, let's not call it that, let's call it just x. Then, and if I've got another point, x prime, which is the coordinates of that point in the other image, in the right-hand image, so these x and x prime would be the two red dots I just highlighted, then the fundamental matrix lets us correspond, if I'm writing these in column form, lets us express this constraint that the left-hand point transposed multiplied by the fundamental matrix multiplied by the right-hand point equals 0. Okay, and because these points are expressed in homogeneous form, this expresses then the constraint that a point in one image lies on a range of points, in other words, a line in the other image, and we'll come back to that. So let's just flip back. So that's a kind of high-level explanation of what the fundamental matrix is. Now let's look at it actually in more detail. So the epipolar geometry and associated constraint that I've just described, I've just put the same figure up again, but I've just basically just changed the notation here. Okay. What we've got here is the point at the top of our tree, the baseline, and these two rays of light. And the baseline is this vector here that goes from the focal point of this first camera, the left camera, to the focal point of the second camera. So that's this red vector here. I've just written that as F1, F2. So that's just the vector there. That's just indicating the vector from F1 to F2. And this purple ray points along the ray of light from F2 to the point. So this is the ray of light from the second camera. This sort of bluey, I think that's blue. I can't tell the difference between blue and purple, so I'm going to call that blue, is pointing from F1 to Y1. That's the left-hand ray. And the epipolar constraint then is being expressed by this equation. Okay, we're saying that if I were to take the cross product of the red line, the baseline, and in this case, let's arbitrarily choose the right-hand ray. If I took the cross product of that baseline and the right-hand ray, they lie on the epipolar plane. So the resulting vector from that cross product would, of course, be orthogonal to both of its inputs. That's what the cross product does. It gives you a vector output that's orthogonal to its two inputs. So it would give you an expression for the normal to that epipolar plane. So if I then take the inner product, the dot product, of the blue vector, the other ray of light, with that normal, it will be 0 because that ray of light also lies on the epipolar plane, and therefore, if I were to take the dot product of a line on a plane with the normal to that plane, it must be 0 because the normal is orthogonal to the plane. So the cosine, will be 90 degrees. Does that make sense? So, that equation there then expresses the epipolar constraint now mathematically. So, right, before I go any further, I want to make sure everybody is okay with that expression. Yeah, is everyone following what's going on here? We've got 3 lines on the same plane. We're crossing 2 of them and then dotting the result, the normal to that plane, with the other one. And that gives us this 0, which means everything must lie on that plane. Yeah? All right. Right, so we're now going to introduce some simplifying assumptions. First of all, when we talk about the epipolar constraint, we're talking about the relative geometry of one camera to another. Okay, we're not actually talking about the relative positions of the cameras to the origin of the world anymore, as we were in the previous lecture when we did the 3D reconstruction and the triangulation. So we're going to assume that the left-hand camera is positioned at the origin of the world, so its center of projection is at 0, 0, 0, yeah, and it's going to be aligned to the z-axis. Its optical axis is going to be aligned to the z-axis, okay? In other words, if I want to figure out, in other words, the extrinsics of the left-hand camera relative to the origin of the world are basically the identity matrix for its rotation is R, and the identity matrix for its translation, or equivalently just a vector of zeros for its small t. Yeah? Is everyone following that? And we're going to say that the right-hand camera, its central projection, I'm now going to use C for central projection for the focus. We're going to call the central projection C prime. We're going to, for the right-hand camera, then that is a rotation then, and the translation from C, from the origin of the world. Yeah? The world frame. So C is at the origin of the world, pointing down the z-axis. C prime is a R and a T off that origin. Yeah? As any camera was that we talked about previously in the previous lecture. Okay. Right. We're going to call X, big X, we're going to say is the coordinates of the point in the world that's being imaged. Equivalently, this ray of light we're going to call X, because if big X is just the coordinates of the point in the world, and C is now at the origin of the world, then this X is just the vector then that takes us to X, yeah, to the point X. It's the offset X's from the origin, yeah, just a 3D vector. And it's going to pass through this point here, and U is going to be the image of that. And similarly, we've got this vector X prime here, which is the light ray on the right-hand side. And U prime is going to be the intersection there. So this is just changing the terminology. There's nothing new on this slide. Okay? Oh, and we're going to call the base... Yeah, we already talked about T. Okay. Everyone happy with this? Now, all of the vectors that I've described there on that previous slide were all defined within the coordinate system of the world, which, as we said, was the coordinate system of the left-hand camera. Okay, so now I'm going to introduce, unfortunately, one final bit of notation, which is a subscript, and the subscript is going to indicate which coordinate system we're talking about. So if I put subscript L, I'm talking about the coordinate system of the left-hand camera, which is equivalent to the coordinate system of the world. And if I put subscript R, I'm going to be talking about the coordinate system of the right-hand camera, in other words, RT. Yeah? Okay. So CL and C prime L are the coordinates of the left and right camera central projections. So on the previous slide, with this new notation, I'd write CL and C prime L there. And in fact, for all of these, I'd write subscript L, because I've talked about them with respect to the world coordinate system and therefore the coordinate system of the left-hand camera. Okay. So let's talk about some sort of simple rearrangements we can make to start reasoning about these quantities with respect to one another. Okay. So the first thing we can see is that if I want to talk about points that are oriented to the coordinate system of the right-hand camera, then that coordinate system is defined by R. So if I have a vector in the left-hand frame, my ray of light, for example, going from the origin of that camera to the point X in the defined in the left-hand frame, then I can talk about it in the right-hand frame by just pre-multiplying by R. And similarly, I can move the other way by pre-multiplying by R inverse. So I can move from the right-hand frame to the left-hand frame by pre-multiplying by R inverse, which is that relative orientation of the right camera with respect to the left camera. Okay. I can also do my projection. If I've got a K, which are my intrinsic matrices of the left and right camera respectively, then I can move from that 3D location of that point I'm imaging to my image by pre-multiplying by that K. And I'm going to say that operation is going to give me UL if I'm talking about the left-hand frame. So if I've got a K here, which is defining the intrinsics of my left-hand camera, then I can go from XL, the image of the point, defined in my left-hand frame, to UL, defined in my left-hand frame by pre-multiplying by K, and I can do the same in the right-hand frame by pre-multiplying by K prime to get U prime R, which is the image of that point in the right-hand view defined with respect to the right-hand frame. Okay, and we're going to make this work. These equations fit with respect to the matrix multiplication by defining them in homogeneous form. So U is as I wrote it, for example, the x coordinate, the y coordinate, and 1. Okay, so. And then we can go the other way, providing we haven't divided through by the homogeneous coordinate. We can go from UL to XL using the inverse of those K matrices. Okay, and that works for both of those equations as well. Right, and this for information is the format of this intrinsics matrix. We talked about this before, all the way back when we talked about that camera projection matrix, that pi. This is what the K looked like. As I say, it was the D's down the diagonal. But because the mathematics allows it, we can have a different D for the X and the Y, a different focal length for the X and the Y, should we want it. And the optical center is encoded as a translation, as we saw previously. Okay, well, let's just put that diagram up one more time. Again, nothing's changed except the notation. Let's just satisfy ourselves we understand this. We're talking about this red vector, this baseline, being T. We're talking about this ray of light here on the right-hand side being x prime, but we're just putting the subscript L in to remind ourselves we're talking about it with respect to the left-hand reference frame. And on the ray of light from the first camera, that's XL as well. And we're saying that XL transposed, previously we just talked about an inner product here, but this is the same. We're just transposing this to the inner product, multiplied by T, crossed by x prime L is 0. This is exactly the same as we had back here when I tried to explain it without this more complex notation. Yeah? Right. I stop there in case there are any questions. Okay. So what we're going to do now is use this notation to derive an expression for the fundamental matrix. Okay, there's that equation again. It hasn't changed. I've just copied it from the previous frame. I've even slide of it. I've even just put in the arrows to make it clear. What we're going to do is try and rewrite this equation here on the top so that we're not talking about rays of light but the images of that point. So we're not talking about the big X's, we're talking about small u's. Ideally, we're going to talk about the U defined within each camera's own local reference frame. So we want to talk about U in terms of the left frame and U prime with respect to the right frame. So let's look at how each of these vectors gets transformed by nothing more than the equations we covered on the previous 3 slides. First of all, we noted that our XL can be expressed as KL, which actually I just called K previously. It's just the intrinsics for the left-hand camera, inverse UL. We saw this here. Yeah. I hope Panopto is recording where my mouse is. And we notice we're transposing it. So all of that's transposed. T, okay, we're just keeping that. Then X prime L. Okay, we're going to first of all express X prime L with respect to the right frame instead of the left. We're going to do that by just applying the inverse of R to it, which lets us move from the left frame to the right frame. And then we're going to unpack that with from XR to project that from XR to UR using this expression here, which again is from the previous slide. So this K prime here, yeah, this is actually not a good way of writing this, because this I've written K prime here to indicate the intrinsics for the right-hand camera, and I've written KL here, so you should probably forget that L if you don't want to overcomplicate your notation, although it's not incorrect. So that then gives us this R inverse multiplied by this second line, which gives us this expansion here. And now we have that epipolar constraint expressed not with respect to these x's, but with respect to these u's, and the u's in each of the coordinate systems of each camera respectively. Now, as we'll see, it's convenient to express this entire line as just matrix multiplications, and we have this kind of awkward cross product here in the middle. But it turns out that that's preventing us from doing so. But it turns out that the cross product itself can be expressed as a matrix transformation. As a aside, if I have 2 vectors, x and y, any 2 vectors x and y that are 3D, then I can calculate their cross product by performing the following matrix multiplication. I can arrange my elements of x as I have in the 3x3 matrix there, and then I just multiply that by y, which is just a column vector there. And that matrix is then a matrix form for the cross product. So what I'm going to do is define this operator with square brackets around it, where this little subscript cross, which means the cross product version of this vector x, which is this matrix here. So that matrix version of x multiplied by y is the cross product of x and y. So I'm going to introduce that there. This is just repeating the line we had on the previous slide, but now I'm just saying the T has been converted into this cross product matrix form. So T is now a 3x3 matrix. So this final expression then, it just consists entirely of matrix multiplications. K was 3x3. This cross product version of T was 3x3. R was 3x3. K was 3x3. That's the K for the other camera. And then we got these 2 points here in homogeneous form. So we can, all of this bit in the middle here to here, is just one big compound matrix transformation. And that is the fundamental matrix. So all of this section here is F. So this then gives us this. Our point on the left-hand side transposed, multiplied by F, multiplied by a point on the right-hand side. Sorry, there shouldn't be a transpose, though. I don't know why there is a transpose there. Delete that, it's a typo. Equals 0. And you can see on the bottom. So we call this F the fundamental matrix. So the F is encoding the epipolar constraint that maps a point to a line. Yeah. Sorry, I was just saying that you can see here that the UL is transposed, but the U on the for the right camera is not, and for some reason I put a transpose there, so please remove the transpose there. And you can see on the bottom line there's no transpose there. Okay, so U transpose F, and then U times U for the other camera is 0. So maybe this slide is clearer. If I have a point on the left-hand side, a point on the right-hand side, they're constrained by this fundamental matrix. So the fundamental matrix then must encode within that 3x3 matrix everything about the intrinsics of both cameras and also the relative position of one camera to the other camera. Yeah? So the fundamental matrix encodes within its values, the intrinsics of both cameras and the extrinsics. Does that make sense? Right, let's stop for any questions on that. Okay. Right. So, it might be useful, and it is useful, to then, having observed then that there's this thing called the fundamental matrix that encodes the epipolar constraint, if we can estimate it, it would be useful to be able to decompose it such that we could get the intrinsics and extrinsics back out of it. Okay? So, for example, if I were to know the intrinsics of my two cameras, and I had the fundamental matrix, what I could do is factor out the K, the intrinsics for each camera, in order to produce this expression here, where we've got K inverse transposed, which is the inverse of K transposed, multiplied by this 3x3 matrix called E, which is actually what we call the essential matrix, which is then multiplied by the inverse of the K for the other camera, the intrinsics for the other camera. Okay, so the intrinsics have been factored out, and this E is containing just the extrinsics. Let me just see. I hopefully do explain that. Yes, I do. So why does this work? Because look at this expression here, which I've just repeated from 2 slides ago. This is the expression for the fundamental matrix. Notice how, remember, the fundamental matrix is given by this compound matrix transformation. Notice how it ends in this K prime inverse and this K inverse transposed. So what we're saying here is just this section contains the extrinsics, and this is the intrinsics for the left, this is the intrinsics for the right-hand view. Okay, and instead of saying, and usually it's written as R TX instead of TX R inverse, and you can just rearrange it like that, because R is an orthonormal matrix. You can do that. It's like A times B all transpose is equal to B transpose A transpose. Which is in fact what I've shown on this slide. So this is showing the mapping then. I was just trying to show with my hand. The U, L, the point on the left-hand side in homogeneous form, transposed is its x coordinate, its y coordinate 1. This is the K inverse transposed. On the right-hand side, this is our point on the right-hand side, and this is its inverted intrinsics. And then what's left in the middle is this TX on negative 1, which is this. This is the essential matrix, which can be rewritten in this form here, just by that transposition rule. So the fundamental matrix then, in summary, is the matrix that relates points in one view to lines in the other view. It can be written just as a 3x3 matrix, or can be thought about as decomposed into the product of 3 matrices, the intrinsics of each camera, sandwiching the essential matrix, which encodes the extrinsics, the relative position of the right camera with respect to the left. And as you can see, when they multiply together, they encode everything about the setup. Okay. So, things we can do with this setup. Well, first of all, if we know the intrinsics and extrinsics of our cameras through some external camera calibration process that we've been talking about repeatedly having access to for the last 2 hours, but we haven't actually talked about how it works. We don't need to know that yet. then it's obviously it's trivial to get our f, because if we know our intrinsics, we can stuff our k with them for each camera. That would be different for each camera. Each camera could have its own focal length and optical center. And if we know the relative orientation and shift of one camera relative to the other, we can stuff those values in our R and our T and therefore get our E. So it's trivial to recover the f from K and E. So, if we did have calibrated cameras, then we could figure out our f and then easily perform this matching operation that we've been describing. Now, if you don't have calibrated cameras and you can't just calculate the f from your knowledge of the intrinsics and the extrinsics via this external camera calibration process we haven't talked about yet, then you can estimate f directly. And in fact, that's exactly what I was doing in my demo. Yeah, I didn't have any information there except just 2 images. And I somehow was able to estimate the fundamental matrix directly from them, from point correspondences between the 2 images. So how did we do that? Well, there's an algorithm which we'll cover now, called the 8-point algorithm, which allows us to estimate f from 8 pairs of corresponding points. It lets us therefore find f directly from point correspondences without knowing the intrinsics and extrinsics of the cameras. So we call this a weak camera calibration. Okay. Why is it weak? Because we're finding the f, but we can't decompose that f into the k and the e. Yeah. Although the mathematics, when we went through, I said we could mathematically, we don't have the knowledge to do that because we start with f, we can't separate it out. Yeah. So a strong camera calibration, we can estimate directly through various means we'll talk about later, the intrinsics and extrinsics, or we can weakly calibrate the cameras by just finding f directly through this matching process. So as a sneak preview, there's a process by which you can figure out the k, the intrinsics for a camera, by showing it the sort of checkerboard patterns and solving a system. Anyway, so let's talk then about this process of weak camera calibration and how we can estimate an f, as my program did, from just 8 pairs of corresponding points. Okay. Actually, the way that we do this is very similar in terms of how we form the linear system as how we solved for the homography last time, when we talked about solving for the warping transformation that would take 4 points in 2D onto another 4 points in 2D. It's a similar kind of thing, but let's just remember that the fundamental matrix and the homography are totally different things. Even though they're 3x3 matrices, they encode different things. So as we've seen, and it's still on the board, the fundamental matrix relates a point on the left-hand side, which we're going to write as uv, to a set of points on the right-hand side that lie on a line. We're going to call those points u prime, v prime. They're in homogeneous form, and the fundamental matrix has 9 values in it because it's 3x3. So this equation then gives us the epipolar constraint. Okay, we can rearrange this into the following form. How can we rearrange this into this form? Well, let's do it on the board, maybe. So, if I were going to multiply, how should I do this? If I multiplied the fundamental matrix with the right-hand point, first of all, then I would get a vector. And what would that vector be? It would be f11, lots of u prime. Let's forget about the subscript I, which is meant to indicate which of the 8 pairs of points we're dealing with. I'll drop that for now. So we've got f11 u prime plus f12 v prime plus f13 times 1. And then on the second row of our vector, we'd have f21 u prime plus f22 v prime plus f23. And then on the bottom, we would have F3 1 U prime plus F3 2 V prime plus F3 3, and then that's the result of doing the fundamental matrix multiplied by the right-hand point, and then what we're doing here is just saying UV1, and it's an inner product between this vector and this vector, which is then going to give us just the number, which is 0, and it's going to be F11 U prime U. Oh, hang on a second, it's more than that, isn't it? Let's do it easier this way, isn't it? U lots of F11 U prime plus F12 V prime plus F13 plus V, and so on. Okay, I won't do it all. But you can see that then the factors on F11 are U times U prime, the factors on F12 are U times V prime, and so on. And you can see that's why we're writing it this way, U times U prime, U times V prime. These are the factors on F11, F12, and so on. Maybe as an exercise to yourselves, you could write that out in full. Okay, and that gives us then this multiplied by this equal this column being our unknowns, what we want to solve for to estimate the F. We want to find F. Okay, and just like we did before, we're going to form a big linear system of the form AX equals 0. Just as we did with the homography, we've got 8 point correspondences here, so I've used the subscript here to indicate now which point correspondence we're talking about, 1 through 8. We've got a row there for the matrix for each point correspondence. So now we have this linear system in the form AX equals 0 that we can solve with SVD just as we did for the homography. And that will give us our solution for F. I'll pause there for any questions. Anyone's got any? You see how we've come to this just by multiplying out this epipolar constraint. We just rearranged it into this equation that we need to solve in order to estimate our F. All of these U's and V's and U primes and V primes, these are point correspondences we know. We've matched those somehow using SIFT or something like that, yeah? Okay? Okay, yeah? All right, so if you remember, this is the slide I put up when we were talking about using RANSAC to estimate a homography. How did we estimate a homography? Remember, we had putative correspondences we'd established between the left and the right image through SIFT correspondence process. We picked 4 points at random in the left-hand image. That gave us 4 points in the right-hand image, just by virtue of the fact that they were corresponded. And then we estimated a homography from those 4 pairs of corresponding points. We then, having estimated that homography H, we applied it to all of the points in order to evaluate how well that homography fitted all the point correspondences. And that was evaluated using this forward-backward transfer error equation. So this is what we had last time. We did it over all n correspondences. So we formed H from 4, and we tested out on all n. And that was our RANSAC process. We can apply exactly the same process here to the 8-point algorithm. We're going to pick 8 points this time at random from a set of, 200 putative correspondences, which were my correspondences in that program. We're going to figure out an F using that 8 we've sampled from them, and we're going to figure out how well that F fits all of them. And that's just RANSAC again, and we can figure out how well they fit just using this equation at the top, just figuring out if they do sum to 0, and so they do give us 0, and if not, it's going to give us a number that's high. So, how does this work? Then for RANSAC for the fundamental matrix, well, I've just said it. I won't repeat it actually. So it's just exactly what I just said. Pick 8 points at random, find the F, apply it to everything. So. Right, in summary then, in this hour, we get through it all, we introduced the epipolar geometry and this thing called the epipolar constraint, which shows us that points in one image map to lines in another image. We saw how that observation, just that lay explanation of it, can be expressed mathematically, and then from that mathematical expression, we can then derive an expression for the fundamental matrix, which is a 3x3 matrix that encodes everything about one camera's view with respect to the other camera. We then saw how that fundamental matrix explicitly encodes the intrinsics and extrinsics when we talked about F decomposing into K, E, and then K from the other camera. And we saw how we can recover the fundamental matrix directly from point correspondences using the 8-point algorithm in a very similar way to how we estimated homographies previous. Okay? So, we have 3 minutes left, which is just enough time, you'll be pleased to hear, to play the fundamental matrix song. Right. I don't know what. Hang on, we're getting a spinning Windows thing. Okay, that's fine. We'll use the non-university laptop.
Fundamental matrix used in stereo geometry. A matrix with 9 entries.
This is just an alternative form for it. It doesn't matter.
Has 7 degrees of freedom. It has a rank efficiency. It's only of rank 2.
This means you can solve it with SVD, as we do.
Matrix F, and you'll see 2 points that correspond. Column vectors called x and x prime. X prime transpose times f times x equals 0 every time. Epipolar constraint involves epipolar lines. Those multiplying f by x results in vector L prime. It's the epipolar line. The other view passing through x prime. The 3-component vector of homogeneous design. The left and right null spaces of the epipoles E prime and P. All of the epipolar lines should pass through these. Easily estimation example, take the same 8-point samples, construct a matrix, take the SVD and the elements of it from the last column of B.
This is 8-point algorithm. Sobel filter.
Set of points, your sample set will be degenerate, that will not bring you joy. When you doing the estimation, if you don't do more rank generation, your epipolar lines, and the epipoles will coincide. But if you're seeing S3 views, the trifocal tensor is what you use. Constraints from the third group act like glue, that has been determined.
So I conclude actually just two points actually to take away from that video are It mentions that the points that you choose to estimate, those 8 points, if you do pick them such that they lie they're coplanar in the 3D world, then the SVD gives you poor solutions. So that's one thing to watch for the 8-point algorithm. And then, there were other things in the song there that we didn't cover, particularly as it went towards the end. It talked about a version of the fundamental matrix that corresponds to 3 views instead of 2, which is called the trifocal tensor, which involves like a 3D matrix of a tensor. But we don't cover that on this course. But it's just to be aware that if you want to scale this to multiple views, you have to do this kind of thing. Okay, great. Well, that's the end of today. So thank you very much.